and welcome to NPTEL MOOC on fiber optic communication systems and techniques. In this module we will look at couple of algorithms, widely used algorithms to estimate the phase phi k. Okay. The problem we have already discussed. The received samples are Rk, which are given in this manner, right. When there is no noise and if you know Sk, then it is easier for you to find phi k, keeping in mind the phase unwrapping problem. If you do not know Sk, then there are problems in applying these algorithms, because the best algorithms can be applied when this parameter Sk or the symbol that you have transmitted is actually known to you. In practice, of course, you send beginning at k equal to 0 or whatever the time instant, you are going to send a certain number of pilot sequences. So, for k equal to p minus 1, all the symbols will be known. So, I am going to write the known symbols as Sk with p at the top here, indicating that this is a pilot symbol. So, these pilots are essentially training symbols which are meant for the receiver to use them to obtain the initial. So, starting at the receiver when it is blind, it just started, it does not know what to do with respect to the phase. So, you assist the receiver by sending these pilots so that it can use them and build up the value of phi k, and from then onwards it can actually go into what is called as decision directed mode. Okay. So, in this mode you can actually track the phase by switching over to this mode, and if your pilot symbols are well chosen, if the channel is reasonably alright, then you will suffer very small change in performance when you go from pilot or training mode to the decision directed mode. Anyway, these are something that we won't be in detail in this course, but you can look at other courses on communication to understand what we mean by decision directed. So, for now we will assume that pilots are known to us and then we want to estimate phi k, right. Now, one of the standard ways of doing this estimation is to perform what is called as maximum a posteriori estimation. I do have some initial knowledge on the phase. If I do not have any knowledge, I can always think of this phase as any random variable between 0 to 2 pi, which means it actually has a uniform distribution 1 by 2 pi. So, this distribution that I have in mind, that is the receiver that knows, is called as a prior distribution, because before receiving any samples I know what this is. I mean, I could, before receiving any sample, this is all the information that I can have about the phase phi k. So, that is why this is called as prior information. But as I start receiving the samples, I can update my knowledge of phi k, right. So, in fact, I can find out what is called as the posteriori distribution, that is after I have received the samples. There will be a probability density function, this will be conditional, okay, and this conditional probability distribution or density function is conditional upon receiving Rk. So, if you do not receive in a particular slot, if you do not receive Rk, obviously you are not going to form or able to form this conditional probability density function, okay. But please remember, this is conditional probability density function of phi k given that you have actually received Rk. And this map criteria tells you that you find this phi k such that this function is maximized. So, you can find that phi k which maximizes this function, which of course puts us right into the problem in the sense that I do not know what value of phi k will actually match or maximize it, right. So, what will it maximize? I do not know. So, I need to know this one, and clearly this is where the difference between actual practice and modeling comes in. All these functions that we are going to write are good for analytical theory, but in practice they are only very good approximations, they are not exactly the same. So, you do not get Nk to be an IID sequence, you do not get this full Gaussian kind of a distribution all the time, especially when the sample sizes are small, but nevertheless you need some handle to begin these algorithms, right, and you need some sort of a performance comparison. So, if these conditions are held, what is the best estimate of phi k, and in practice how you deviate from that phi k is entirely dependent on the actual channel. Okay. If your algorithm is good and robust, then the difference between what you get in theory or what you compute in the numerical way would be more or less same as what you are going to get in the actual practice. So, with that in mind, so we would like to find out what is the conditional probability density function of phi k and then maximize that one. But because I am assuming any value of phi k is possible, right, I do not have to worry about this maximum a posteriori probability, but I can simply worry about what is called as maximum likelihood. Okay, where do I get this maximum likelihood? Maximum likelihood is essentially obtained by first going into or first using Bayes theorem and transforming this conditional PDF of phi k given r k into r k given phi k. Okay, so I am transforming this PDF into this manner. Of course, I need to multiply by phi k and then divide this entire thing by f of r k. This f of r k is the PDF of receiving the symbol, and it does not really have any statistical nature to it. So, it is just the receiving probability. So, you do not really worry about this one, and because you said that f of phi k, that is conditional probability density, or rather the prior probability distribution function or the density function is uniform, any value of phi is allowed between that 0 to 2 pi, the thing that we are going to maximize is this particular probability, and this probability is called as likelihood function. Okay, so although this is a PDF, this is called as likelihood function. Frequently you will find out that people actually use what is called as log likelihood functions. Okay, so this is sometimes called as log likelihood ratio when phi k can take on only discrete values, but here phi k is not discrete value, therefore I would not want to use the word ratio here, but this is a standard terminology, so we may as well keep that in mind. Okay, so I am going to use this likelihood function, and my rule of finding the best estimate of phi k is the one which will actually maximize this probability distribution or density function. So, find the phi k such that it maximizes this particular function. Okay, so this is called as maximum likelihood estimation, and this is what we are going to do. So, what is the conditional distribution function of r k given phi k? Well, if r k is given by s k e to the power j phi k plus n k, first let us think about this in terms of a vector. Okay, so in the in-phase and quadrature space that I have, these r k, n k are all going to be vectors. So, first let us assume that I have transmitted this symbol, which is say skp, so that is the vector here, and then because of the phase noise, this vector has moved and become e to the power j phi k. So, this is the phi k that you are actually estimating. So, this difference is the phi k that you are estimating, and please note that by multiplying sk with e power j phi k, you are only going to move it in a given circle. So, this is actually a circle, and you have moved a certain distance depending on what is the actual value of phi k that has been realized at this particular sampling interval. Fair enough. So, we have this as the point. Okay. Now, there is a noise. Noise could actually be added in any direction, meaning that it has both in-phase and quadrature component, and therefore its amplitude could be some value which is a magnitude, but then the phase could be anywhere up there. So, after you assuming that the noise as realized in this particular way, the width around this point is actually determined by the variance of the noise. This is what the actual received symbol here for you. So, this is the received symbol r k after taking noise into account, and this little red line here which I am redrawing is your noise vector n k. Please note that noise is also complex, so it can also have a magnitude and it also has a phase phi n k. Okay, so, this is what the received vector is, right. As long as these phi k and n k are reasonably within their limits, then I can actually look at what is r k, find out what is s k. I could look at the distance and then be reasonably assured that I am in the right decision space. Okay. But in case the phase phi k is larger, then this received vector r k would go into a different quadrant, and then you may not be correctly estimating the phase, because if you estimate the phase to be smaller and different, then it will not bring it back to the actual constellation that you have transmitted, and therefore you will start making errors. Anyway, so this is the vector picture of this one. Keep the vector picture in mind. We are going to return to the vector picture shortly after we write this equation. So, if you go back to the real kind of a case, if this is r k that you have received and this is the s k e power j phi k skp e power j phi k that you have transmitted, the difference in the complex domain or this vector n k is the amount of noise that has added. And what is the probability of generating this noise? Is that noise probability dependent on r k? No. Is the noise probability dependent on skp? That is also no. So, this can be reconverted into unconditional probability density function of the noise alone of being a certain amplitude which is given by r k skp e power j phi k. So, this is how you can actually get the likelihood function expressed purely in terms of the noise. Okay. And we know what is the Gaussian noise with an amplitude factor of Rk minus skp e power j phi k going to be, right. This is equal to 1 by 2 pi sigma n square under root e to the power minus Rk minus skp e power j phi k magnitude square. Please remember, this is a zero mean process, therefore the amplitude magnitude square divided by 2 sigma n square is what will be the probability density function that I am interested in. So, this probability density function is actually the likelihood function that you now have, and you want to maximize this likelihood function. How can you maximize the likelihood function? Look at the exponential function. The exponential function will be maximum when its argument is actually 0. So, which means that if you can maximize this, or rather minimize this difference, right. So, when you make this difference to be as small as possible, then that would maximize this exponential function. Alternatively, you could actually expand this out and then get Rk square plus skp magnitude square, because clearly e power j phi k magnitude will be this one. So, 2 times real part of Rk skp conjugate e power minus j phi k, and then you want to minimize this fellow, right. Minimizing this means you want to maximize this quantity, right. So, you can actually come down to simple correlation of your received samples with the pilot sequence multiplied by an unknown e power minus j phi k, and that would actually give you the total or estimated phase phi k. Okay. So, that is what you can actually obtain. So, that particular phi k, you may not know this, but you know what is this one, right. You know what is this skp. So, you try out various values of phi k. So, over 0 to 2 pi, you try out some 10 samples up there, and then when you multiply each of those samples by e power minus j phi k after conjugating the known sample sk. So, this is known to you, this is what you are actually trying. So, therefore, this is also known to you. Rk is what you have received, therefore, this is also known to you, and then you take the product of these guys to obtain the correlation, take the real part of it, and whatever that would maximize this product will be the estimate phi k. Okay. So, this seems to be the method for going for a single symbol case, but in case you actually receive, let us say, over p training symbols as we called. So, this is S0p to SP minus 1p. So, these are the received symbol sequence that you have obtained, and assuming that the phase is going to be constant, right, then you also have a corresponding R0 to Rp minus 1. Then what you can do is, you can take Rk minus I, Sk minus I p conjugate, and over this range the phase is actually constant, that is, you are actually looking for the average phase corresponding to this one. So, this is the this is the average phase phi k. So, I have the average value which is independent of, or which is constant over the entire symbol, and then you sum this over I equals 0 to p minus 1, and what you get is this particular quantity, which is the inner product of the received sample sequence with that of the training sequence, right. So, with that of the training sequence, if you take the inner product of these two, or the dot product of these two, then the argument of this. So, if you actually look at this way, this is the inner product. So, I can express this inner product as its magnitude. I will call this sequence as, say, without this phi k, I will call this sequence as uk comma p, p standing for the length of this sequence, k standing for the sequence at the kth time. Of course, as k increases, you have to keep moving this block of p symbols away from each other. So, I have uk comma p, and then argument of this uk comma p, which is the inner product of the received sample sequence with skp. So, I can even write this in this usual manner, ukp magnitude e power j angle of uk comma p, okay, multiplied by e power minus j phi k average is what you would have obtained as the exponential function up there. So, you take the real part of this and then call this one as the estimate phi k hat. So, clearly when you take the real part of it, magnitude will be constant. So, that would simply come around here, and then you have cos phi k hat, which is the estimate minus phi k average, right. So, the estimate phi k that you have obtained, which is basically the argument of uk comma p will be the best estimate for the average phi k of the phase noise at that particular kth sampling time. So, if you now move on to say k plus 1, then you need to move this block. So, you actually have received symbols, you go back in time. So, this is rk minus 1 and you go all the way up to rk minus p plus 1. So, that is the length over which you are actually looking at the received samples, and then if you know these values sk sp minus 1 of k, or rather s, so same values, right. So, it is actually going to be sk minus p plus 1 the pilot sequence. So, if you know all these pilot sequences, then you can take the inner product or generate the vector out there, and then the argument of that inner product will be the average phase that you are actually looking for. So, this is more implementable version than the previous one. The previous version was called as blind phase search, because in this case you did not know what phi k was, but you assume that phi k could be changing every time. Therefore, every symbol that you obtain, you actually can do a blind phase search by stepping through all values of 0 to 2 pi in appropriate intervals that you have, and then maximizing this particular inner product. But when you extend this into this form, this is called as block phase estimation, because you are actually looking at a block of p symbols, and when you know all the pilots in that particular block, you take the inner product of the received symbols with the pilot symbols and then call this as your estimate. Please note that in this case we have assumed phi k to be slowly changing. So, which means that this is reasonably okay to apply to the case of high bit rate systems. The performance metric that you are looking at will be again the BER, and that will actually depend on the sample or the block length p. Okay. So, there will be some optimum value, BER is actually going to decrease and increase. So, there is going to be some optimum value of p for which BR is kind of minimum, and then you can work with that. That would be the optimum block length. Too large a block length means you are actually assuming that many symbols have the same phase, which is absolutely not okay, but too small link may not satisfy. Too small block length may not give you that statistical fluctuation that you are looking for. Noise will not be there to average it out, and therefore your performance will suffer. So, there is an optimum block length which lies somewhere between too small p and too large p, which will give you a best phase estimate phi k. You can now see that there has been a problem in all our technique that we have discussed. The problem is that I should know the pilots. Now, if someone does not give me pilots, or after the pilots have exhausted, I can either do this decision directed mode, or I have to look for other methods when pilots are not at all available. Okay. There is an important technique which has become the benchmark technique called as Viterbi algorithm. Just as DBP is the benchmark technique for CD, VVCPE has become the method for phase noise. Sometimes the decision directed maximum likelihood that I just described previously is also used, but this one is much simpler, and this is a method which we call as blind, because it does not require any pilots. The idea of this one is very simple. See, first assume that there is no noise. So, you have Sk e power j phi k. Please note that I am not writing this p here, because I do not need to know the pilot here. I mean, there is nothing I need to know, except I need to have a constellation which is of the form m array psk, of which the simplest one is qpsk. You could either have symbols arranged in 45 and differences of 90 degree again that way, or you can actually have these symbols, right, the ones that are shown in blue, but nevertheless all of these actually fall on the same circle. Although I have not shown you the correct circle, they all fall on the same circle, which means they all have the same magnitude on that one. So, these are also called as constant envelope signals. Of course, noise will be present. So, what would noise do? Noise would actually take this amplitude and make it lie anywhere in between these values, right. So, it would actually make a bulge region around that one, and when you have finished looking at the phase and estimating the phase correctly, you are going to obtain this kind of a constellation. So, these are all going to be circles. So, the signals could lie anywhere in between, but because they are reasonably separated, the BER will be considerably less in this particular case, and these circles actually are the variances, or determined by the variance of the noise. Anyway, so the point is that in an ideal system, the envelope of the QPSK signals will be constant, and because QPSK is used currently in 100 Gbps system, this technique is very important for us to learn. The technique is very simple. Assume initially that there is no noise. Now what I do is I take this Rk, raise it to the power 4, right. In general I will raise this one to the power m, but for now for the QPSK I will raise it to the power 4. Once I have raised it or raised this Rk to the power of 4, what I have actually done on the right hand side is I have raised this one to the power of 4, e power j phi k to the power 4 is basically 4 phi k. Now what is Sk power 4, right? If you look at this one, this is all given by e power j 2 pi by 4, right? So k will be, or n, so n will be say 0, 1, 2 and 3 when you actually look for, so with 0 that would be at 0, so when it is 1, no, this is actually going to be 2 pi by, I have to create these points, right. So this is 45 degrees and therefore I need n equal to 1 to begin with, and then when n is equal to 2, anyway, so these are the 45 degrees and then 135 degrees and so on, but when I take them to be the power 4, yeah, this is n equals 1, 2, 3 and 4, let us say these are fine. Then when I take the first one is e power j pi by 4, the second one is e power j pi by 4 plus pi by 2, right, and then e power j pi by 4 plus pi, and then you have e power minus j pi by 4. So these are the 4 constellation points that I have, and when I raise them to the power 4, I am going to multiply everywhere by 4. Okay. So when I multiply them by 4, 4 and 4 will cancel, 4 and 4 will cancel, and then this will be 1 and this will be 2 pi. So e power j 2 pi is 1, so I will get this as e power j pi, this will be e power j pi, this will be e power minus j pi, this will also be e power j pi. Minus j pi is the same as plus j pi, because all these values after raising them to 4 will give me 1, or rather minus 1. Okay. And that is not really important, minus 1 or plus 1 is not really important. If you do not want it to raise to the power 4, you raise it to the power 8 and you get rid of this minus sign and make it plus 1. But the important point is that you got rid of this Sk power 4. I can take this to be a constant, or I can take this to be plus or minus 1 depending on what value I have raised this particular thing, and that depends on the kind of constellation. For this constellation, raise it to the power 8, and for this constellation, that is on these axes which are given by e power j 0, e power j pi by 2, e power j pi, e power j minus pi by 2, you raise it to the power 4 such that everything will converge back to plus 1. Okay. So what you have done is, without knowing what one of the 4 symbols that I have transmitted, you have converted that Sk power 4 either into plus 1 or minus 1, but in both cases the effect of modulation has been removed, right. So we have removed modulation effect by simply raising it to the appropriate value of constellation, in this case 4 or in some cases 8, but these are done without knowing what has been transmitted. That is a big difference, because if you do not know what you have received and yet you are able to remove the modulation, that is a very good point of that, right. But you do not know what is the phase, which is okay, we are going to estimate it now. How do I estimate it? I know what is Rk power 4, that should be equal to e power j 4 phi k, right. Now if I take the argument of this or the angle of this one, then taking the argument essentially means I am going to have 4 phi k here, right, which is more than what I want. I want phi k, not 4 phi k. So I can actually take this 1 by 4 onto this side and then get phi k, right. This is a very simple way of obtaining the phase estimate phi k. So once I obtain this phase estimate, I am going to go back to the received signal Rk, I multiply it by the phase estimate phi k. What is the result of doing this one? So I had originally Sk e power j phi k, which was unknown. When I multiply this one by e power minus j phi k hat, and if this estimate and phi k are essentially close to each other, then the product will be equal to 1, and what you get here will be just Sk, which is my symbol that I have, and this can go to the decision device, right. So this is as simple as that. So this method can be applied for any m-ary systems which have which are divided by 2 pi by m angle apart. So when you raise them to the power m, that is actually equivalent of multiplying it to m and then removing this. So modulation can be removed, and once you have removed the modulation, you take 1 by m of the angle at any point of the angle at any sample point Rk, which has been raised to the power m. Now this was without noise. In that case everything works out fine, but what do you do with noise? Well, noise is additive white Gaussian noise. So it has equally a probability of being positive and negative. So what you can do is to average these symbols. Again, you can form a block. Okay, so you have rk minus 1, let's say rk minus l plus 1, L length block you can take. Again, you don't need to know any of your transmitted sequence. All that you have to do is take the average of this. So rk summation k equals, or rk minus I, let's say, where I is equal to 0 to L minus 1, right? So that rk minus L plus 1, yeah. So this is correct. So you just take the average, then take the argument and then divide it by m being the M-Array phase system that you are looking at. So this way you can reduce the effect of noise by simple averaging process. Okay, and it turns out that this method, which does not require any feedback, because in decision directed methods you want a feedback, you want to know what has been detected and use that to estimate. So this is called as detection plus estimation problem, whereas in this problem you are not looking at any detection part. I mean, there is now no information coming from the decision device back to the estimation algorithm. All that is coming back, or all that is there happening is one way propagation or one way flow of information. So in that way I start off with a symbol or a block of length rk. Again, that length L depends on the application, and again the BR will be optimum for a given value of L. And then once you have that value over that range L, you simply average the received symbols and then take the average or take the argument of that one, divide that argument by m. You still have to deal with the phase unwrapping problem, but that anyway has to be dealt with every phase estimation algorithm. And then once you have done that one, you can decide the symbol by derotating rk, right. So this method is called as feed forward carrier phase estimation method and is very, very popular for the case of simple QPSK type of systems. But when you go to a QAM system, then it is still possible to use these methods, except now you have to decide which ring you are on, right, because in a 16 QAM system, for example, you will find that there are amplitudes which are of 3 levels. So you have 3 different rings. So there is usually a ring indicator or intensity indicator. Using that as an information, you can then decide the same kind of an algorithm, or you can partition the signal set into those amplitude levels and adjust it slightly, and then come up with what is an algorithm called as multi-modulus algorithm, which is a generalization of this Viterbi algorithm. Anyway, this finishes our talk or our algorithms about carrier phase estimation. I encourage you to actually work out these algorithms using MATLAB or any of your preferred programming choice. Thank you very much.